All right, time for part C, the last short answer questions. So 66 through 68. Compare. Whoop, whoop, whoop. Love a compare question, right? So compare the number of protons to the number of electrons in an atom of oxygen 18. Well, I don't quite frankly care. It's an atom of what? If it is an atom, it is neutral, right? And since protons are positive and electrons are negative, the number of protons and electrons must be equal. So the number of protons and electrons must be equal in atoms. That's just the rule. 67. In the space in your answer booklet, draw a Lewis dot diagram for an atom of oxygen. So just as a reminder for 67, this is what it's going to look, a big space. So oxygen, if you don't remember, let's look it up on the periodic table, has 6 valence electrons. That is what I need to show on the Lewis dot diagram, right? So I can do it here. All right, so an electron dot diagram for an atom of oxygen. Here is oxygen. I need 6 valence electrons. 1, 2, 3, 4, 5, 6. Ta-da, like that. 68. State in terms of neutrons. So I literally got to say the word neutrons. Why a water molecule containing an O18 atom has a greater mass than a water molecule containing an O16 atom. So if we have O18 and O16, right? We look it up on the periodic table. Oxygen's atomic number is 8. So I don't care if it's oxygen 18 or oxygen 16, it has 8 protons. So when I subtract these, that tells me the number of neutrons. So why a molecule that has oxygen 18 would have a greater mass? Because oxygen 18 has more neutrons. So oxygen 18 has more neutrons. I could say it has 2 more neutrons, but I don't have to. I just have to say it has more. Or oxygen 16 has less neutrons, so it would have less mass. Okay. And then we have 69 through 71. Show a numerical setup for calculating the percent composition by mass of oxygen in the sodium hydroxide carbonate. And it tells me the gram formula mass. So from the reference tables, right, I need percent composition by mass. So here we are for question 69. So 4% composition by mass, I have mass of part over mass of whole times 100. So I have mass of part over mass of whole times 100. Now, I was given the gram formula mass, and the gram formula mass is the whole. So now I know that the whole is 84, right? I need the part, okay? And I got to keep the times 100. So it was asking me to find the percent composition by mass of oxygen in this, right? So here is the formula for sodium hydrogen carbonate, right? How many oxygens are in that formula? 3. What is the atomic mass? The molar mass of each oxygen, each mole of oxygen, 16. So the total mass for the oxygen piece is 3 times 16. So 3 times 16. Now I can be done. That's it. I can leave it just like this because it just asked me to show a numerical setup. I can be done. Ta-da. Don't do any of the math because if you make a mistake, potentially you could lose points. That's it. I could leave it as 48 over 84 times 100, but I don't have to. This is good enough. This is also correct. Okay. And number 70, determine the number of moles of K2CO3 produced when 3.5 moles of KO2 completely reacts as represented in the equation. Okay, so I have 3.5 moles of KO2, and I want to know how many moles of K2CO3, right? So I'm going to, find the equation, and what is, it says equation 1, so I got to look here. What is the coefficient in front of KO2? 4. What is the coefficient in front of K2CO3? 2. So now I just cross multiply, right? 3.5 times 2 is 7. This is what I'm trying to find, 4 times x, right? Then I'm going to divide by 4. So what is 7 divided by 4? 1.75 volts. Okay, now 71 is balanced in an equation. So here's my equation, which looks complicated, right? So let's just make a list of elements. We have Na, H, C, and O. So Na, H, C, and O. There's my divider, right? So over here I have 1, 1, 1, 3. On this side I have 2, 1, 3, 2, another 1. Here I have another 1, and then 2. Oh my goodness gracious. So this is 2 total carbons, right? And this is 6 total oxygens. Oh, good gracious. This is a hot mess, right? Okay. What I'm going to try to do is, I don't even know. Okay. I'm going to put a 2 in front of this because why? I have 2 NAs here and 2 H's, and I only have 1. So I'm going to try it. Let's see what happens. Let's put a 2 there. When I put the 2 there, I multiply this times 2. It also multiplies this times 2. It also multiplies this times 2. And it also multiplies, oh my goodness gracious, look at that amazingness. Everything else is balanced. Ugh, who knew? Now I can leave everything blank. Or if blank stress you out, 1, 1, 1. Or leave them blank. Totally fine. All right, question number 72 and 73. 72, determine the volume of this sample of helium gas at 350 Kelvin. So that's this point, go across, it's right here. So what do I put? It's maybe, this would be 5.5. This is 6. So like 5.8 liters. Fun fact, what they accepted on the answer key, right, is anywhere from 5.6, so definitely it was not on the line for 5.5, right, to 5.9. And it was definitely not on the line for 6. So this, they gave amazing grace for what the answer could be. Number 73. Compare beautiful, love it, right? Either equal or greater. Compare the average kinetic energy of the helium atoms in the sample at 200 K to the average kinetic energy of the helium atoms at 300 K. I literally love this. What is average kinetic energy? Temperature. So look at this temperature. Look at this temperature. Okay. So the average kinetic energy is greater in the 300 K sample, right? Because it has a higher temperature. That's it. That's all I got to say. I mean, you could word it a different way. Say the average kinetic energy is less in the 200 K sample. There's more kinetic energy in the 300 K sample, right? There are lots of ways to word it, but that's really the answer. Okay. All right, 74 through 77. We're getting so close to the end. Here we go. Explain in terms of, okay, so collision theory. So that means I got to talk about colliding, right? So explain in terms of collision theory why reacting hydrogen and nitrogen at high temperature increases the rate of the reaction. So the answer, whenever rate of reaction increases, the rate of reaction increases because there are more effective collisions. Now, I could just say more collisions, right? But more effective collisions is like the truer, right? But the rate increases because there are more collisions. How do you increase rate? Increase collisions. How do you decrease rate? Decrease collisions. All right. Determine the net quantity of heat released when 1 mole of ammonia gas is produced by this reaction. So if I look up here, I don't see anything about a number except for here. Aha. Okay. So it says when 1 mole of NH3 is produced. So I have this number of kilojoules released, right? But look how many moles of NH3 were produced. So how would I determine how much energy was released when I had 1 mole? Well, it literally would be half that, right? So I would just do 91.8 divided by 2. Why? Because 91.8 for 2 moles, but I only have 1 mole. So 91.8 divided by 2 is 45.9 kilojoules. So 45.9 kilojoules. Number 76. Using the axes in your answer booklet, draw a potential energy diagram for the reaction. Okay, so before I even go there, let's think about what I need to draw. This is the energy, right? And it is on the product side, which means it is exothermic. Energy is coming out. If energy is coming in, it's endothermic. If it's going out, it's exothermic. So let's go to the diagram. Okay. All I need to do is draw a potential energy diagram that starts with reactants, goes up until I reach the activated complex, and then I need it to be exothermic. So I need it to come down like that. And that's it. It was that simple. And 77, state in terms of activation energy and reaction pathway. 2 things I got to say in my answer. Why the addition of a catalyst increases the rate of the production of ammonia. So a catalyst, it's basically the definition of a catalyst, provides an alternate, right? An alternate reaction pathway with a lower activation energy. That's literally the definition of a catalyst. Okay. Getting closer, 78 through 81. Identify 78. Identify the element present in the reactants that allows them to be classified as organic compounds. Literally carbon. Bam. Okay. Write a chemical name for reactant 1. So here's reactant 1. Where do I find help with naming this? I got to go to table. So go to table R. And now if you see, I'm looking for something that ends with COOH. So this just ends with OH. No, this is COH. Aha, look at this. COOH. Okay. So that's an anoic acid. So the name is going to be something anoic acid. What do I have to put in front? Well, let's look at the reference table. This is prop because I have 1, 2, 3 carbons. So how many carbons are in this reactant? 1, 2. What is the prefix for 2 carbons? F. So if I go back here, the name of this would be ethanoic acid. Number 80, write a formula for the missing product X in the equation. So I got to figure out what's missing, right? So here are where the 2 sides of the equation are, all right? Let's start with this. Let's count carbons. 1, 2, 3, 4, right? How many on this side? 1, 2, 3, 4. Oh, okay, so I'm not missing any carbons. All right, let's pick a different color. Let's pick this light purple. Hydrogens, 3, 4, 5, 6, 7, 8. 3, 4, 5, 6, 7, 8. And then I was like, what is happening? But this, I missed this. So I'm missing 2 H's. So I'll go through that again. So that's 3, 4, 5, 6, 7, 8, 9, 10. 10 hydrogens on this side. But this side I have 3, 4, 5, 6, 7, 8. So see, I'm missing 2 hydrogens. All right, now let's pick another color for oxygen. 1, 2, 3. On this side, I have 1, 2. So I'm missing 1 oxygen. So what would the formula be for the thing that's missing? H2O or HOH. 2 hydrogens and 1 oxygen. All right, and 81. Identify the class of organic compounds to which this belongs. All right, that is table R. So what am I looking for? I'm looking for some carbons over here, some carbons over here, right? And in the middle, I've got 2 oxygens. So here, this is the only one that has 2. See, this has 2 oxygens, but it's got a hydrogen on this end, and I need carbons. So 2 oxygens in the middle with carbons on either side. That class of compound is an ester. Okay. And our last section, 82. Compare, love a compare, right? Compare the penetrating power of the beta particle emitted from the iodine 131 nuclide to the penetrating power of the alpha particle. Well, the penetrating power of the beta particle is greater. Okay, why? We'll just look at table O for a minute. Here you can see alpha particles have a mass of 4, whereas beta particles have a mass of 0. So beta particles are able to penetrate through more things. They get blocked by less. Okay. Number 83, complete the nuclear equation in your answer booklet. So let's go to the answer booklet right here. Here, for our purposes, that's where the equation is divided. So on this side, I have 59. On this side, I have 0 so far. So my top number has to be 59. And the bottom, I have 26 on this side. And that has to be equal to -1 plus whatever my mystery number is. So I have to add 1 to both sides. So it should be 27. So I have 2 numbers, but now I need a symbol. So I need to go to the periodic table, and that is cobalt. Okay, that is the correct symbol. Be careful writing a capital C and a lowercase o. Number 84, determine the fraction of the original sample of the radioactive isotope used to test for thyroid problems that remains unchanged after 24.063 days. Well, I didn't even have to remember it. Look, it says that's the one that's used for thyroid, right? And determine the fraction. So let's just go through. First, if in a fraction, I start with 1, the whole thing. Then I would have a half. After another half-life, I'd have half of a half, which is a quarter. After another half-life, I would have a half of a fourth, which is an eighth. After another half-life, I would have half of an eighth, which is a 16th. But I need some reference table information. So from table N, iodine 131 has a half-life of 8.021 days. So that means this took 8.021 days, right? but I need it to go for 24 days. So this also took 8.021 days, which that's about 16. And this took another 8.021 days. Aha, that's enough. So 8.021 times 3, right, is going to give me this. So that means this half-life happened, this half-life happened, and this half-life happened. So what fraction remains? 1/8. And then our last question, finally, determine the number of neutrons in an atom of Am 241. So remember, the 241 goes at the top, but I need the atomic number because I can't do that without the atomic number. So I need to find it. Here it is way down here. There is its atomic number. It is 95. So if this is the mass number on the top, 241, which is protons plus neutrons, and this is protons, I subtract those numbers. So 241 minus 95 equals 146. That is how many neutrons I have. And there we go. Phew! We made it through the whole exam. Congratulations.